All right, let's get right into it. We're going to peel back the curtain on a piece of technology that most of us use every single day, but probably never think twice about. We're talking about the incredible and kind of invisible engineering that keeps us safe inside an elevator. I mean, think about it. You step into this little metal box, you push a button, and you just trust it. You completely trust it to carry you, hundreds of feet into the air. It's this little act of faith we all do, sometimes multiple times a day, without even blinking.
But here's the thing. That trust isn't built on luck or hope. It's built on some serious physics, materials science, and incredibly precise calculations. So today, we're going to dig into the hidden forces at play. And we're going to use the work of engineering specialists like Novan Poya Elevator as our guide to see exactly how those forces are mastered.
So let's start with something that's kind of hiding in plain sight. Yep, those simple-looking metal tracks that run all the way up and down the elevator shaft, they do way more than just guide the car. They are the backbone of the whole system. They have to absorb and transfer every single force the elevator deals with, from its own weight to you shifting your feet, and channel it all safely into the building itself. They are, no exaggeration, absolutely critical. Now, here's where it gets interesting. These guide rails are constantly in the middle of a battle between two very, very different kinds of forces.
On one side, you've got static forces. This is the easy part, relatively speaking. It's the predictable weight of the car, the people, the counterweight, all stuff you can calculate pretty straightforwardly. But the real challenge, and I mean the thing that separates okay engineering from great engineering, is mastering the dynamic forces. These are the sudden jolts, the shifting weight, the immense power of an emergency stop. They're unpredictable and they're powerful.
And that brings us to a really crucial point. What actually happens if you get those calculations for the dynamic forces wrong?
Well, this is where the stakes get incredibly high. Even a small error can create a ripple effect. It might start as something you just feel, an unsettling vibration, maybe a weird noise. But over time, that constant stress causes parts to wear out way faster than they should. The guide rails themselves can actually bend permanently. And in the absolute worst-case scenario, well, it can lead to catastrophic failure. It's why precision isn't just a nice-to-have, it's a must-have.
So, how do engineers actually get this right? How do they account for forces that are so unpredictable?
Let's look at two of the big ones, starting with something called eccentric loading. It sounds technical, but it's actually super simple. Just picture everyone in the elevator deciding to huddle in one corner to take a group photo. That lopsided weight creates this twisting, sideways pressure on the guide rails. It's kind of like trying to carry a really heavy, unbalanced shopping bag. It just wants to pull you over. Engineers have to plan for the most extreme version of this and make sure the rails can take it without even breaking a sweat.
And then you have the big one, the safety brake impact. This is the force you hope the system never, ever has to deal with, but it absolutely has to be ready for. When that emergency brake slams on, it doesn't just halt the car. It sends this enormous, instantaneous shock load. We're talking many, many times the elevator's normal weight straight into those guide rails. The whole system has to be built to withstand that incredibly violent jolt and come out the other side perfectly fine. Okay, so understanding these forces is one thing, but actually designing a system to handle them, that takes a really specialized approach. So let's take a look at the process that a firm like Novan Poya Elevator uses to see how the pros do it. See, instead of just relying on old-school, basic calculations, they used a multi-step method. It starts with advanced dynamic simulation software. This basically creates a digital twin of the elevator, letting them model all those real-world forces before anything is even built. Then, they use something called finite element analysis, which is like putting the guide rails under a digital microscope to see exactly where and how stress builds up. This whole data-driven process just removes all the guesswork. But of course, all that brilliant analysis doesn't mean a thing without the right hardware. All that sophisticated modeling leads to the final, and maybe most important step, choosing materials that can actually handle what the numbers say they have to. By using premium, world-class guide rails from top-tier makers like Monteferro and Marazzi, they're making sure the physical reality matches the engineering rigor. So, when you put all these pieces together, what does it all really mean?
I think this just says it all, right? True safety, the kind you can bet your life on, doesn't just happen by chance. It's the deliberate, calculated result of deep analysis, rigorous planning, and an absolute refusal to compromise. It has to be engineered, from the ground up.
You see, this is a whole different way of thinking about safety. It's about accounting for every weird vibration, every possible imbalance, every single worst-case scenario. Not because it's likely to happen, but because it could. And that deep commitment to meticulous analysis, that's what transforms a simple box on a rope into a truly safe, reliable system that you can trust for decades to come.
So I'll just leave you with this. The next time you're in an elevator and you push that button and you feel that smooth, quiet ride, just take a second. Appreciate that silent, powerful battle of forces that's being fought and won on your behalf, all thanks to some really brilliant and totally essential engineering.